So what we're going to start looking at now is this idea of complex numbers in polar coordinates. So you guys are starting to find that as you get into higher and higher math classes, you take things you've done before and you do them in different number systems. Okay? You take the same basic 4 operations, adding, subtracting, dividing, multiplying, and you do them in a bunch of different coordinate systems. Okay? So it's the basic principles of math. You do them in different things. So what we're going to look at now is complex numbers in polar coordinates. So quick review in the complex plane or in rectangular. So we got a real axis, we got an imaginary axis. We call complex numbers with the z, okay, just something they came up with. Now this book uses an x plus yi. The Algebra 2 book, we always had a plus bi, okay, but they mean the same thing. So we know I represents the complex number. It's for things like quadratics like this that never hit the x-axis, so we need some way to get solutions for them. But what we want to look at is how we're going to find absolute value of z. Now, Algebra 2 book calls it absolute value. This book calls it the magnitude. Okay, it's the same thing. So you guys know absolute value is just your distance from 0 in a straight line. The way we get that, again, is just a simple Pythagorean theorem problem. We had to go over x, we had to go up y. That'll tell us this magnitude right here. So all we have to do is magnitude is just square root of x squared plus y squared. Now remember, let's say if something's over here, let's call this like -6 -6 plus 10i. If you were to find the magnitude of this, this is -6, this is 10. Make sure when you're squaring this, you don't get -36. So make sure this guy always comes out as a positive. Okay, you'll never have to deal with negatives when you're doing these magnitudes in complex numbers. Okay, I don't even include the negatives because I know it's just going to square and make a positive. Okay, so that's how we find magnitude. If we want to do this in a polar plane now, we got to go back and look at conjugates. So remember, a conjugate is, if I gave you something like this, 3 plus 2i, its conjugate is just 3 minus 2i. So if the original is x plus yi, the conjugate, we use this little notation here, z with a bar above it. So it's an x minus a yi. Now, when you multiply conjugates, they have interesting properties. So let's take this example here. And when we double distribute it, middle terms go away, we're left with this. But by definition, I squared to -1. It's the whole idea of complex numbers. So when you multiply conjugates, you can get the i's to go away. Okay, so same idea here. If we took these two things right here and we double distributed them, we would get the same thing we just did, just with variables instead of actual numbers. You'd get an x squared plus a y squared. So if we take the original multiplied by the conjugate, we just get x squared plus y squared here. So the magnitude of that guy is just square root of original times conjugate. Okay? So if we know this is the same thing as x squared plus y squared, we can just do a little substitution here and say magnitude is the square root of these guys. Because really, that's what they're doing. Okay, if we want to write these in polar form, we don't use x's and y's, we use r's and thetas. So here's the thing in Cartesian form, x plus yi. Over here's how we do this in polar form. all they did is say an x in polar is an r cosine theta. And we've done that for a couple days now. They say a y is the same thing as an r sine theta. And then you just add the I on there to make that guy complex. They factor the r out to write it a little simpler. And here's how you write a complex number in polar form. R cosine theta plus I sine theta. Okay. Now, if you want to take this and create some magnitude out of it, so basically take this guy here, find the magnitude of it. So we plotted something in polar, we want to find the magnitude of it. If you'll remember, magnitude is nothing more than the square root of x squared plus y squared. But if we're in polar now, this is our x, this is our y, with r's and cosines and sines now. So really, we just have to take r cosine, square it. We got to take r sine and square it. Notice there's no I in there anymore because we didn't use the i's when we found absolute value. In the very beginning, we ignored what little the I there, and we just take the values of the numbers. So if we do this, r squared cosine squared, r squared sine squared, you factor out that r squared again, our most basic identity tells us that guy's a 1. If you square it the r squared, you just get an r. So therefore, magnitude of a complex number in polar form is just the radius. Here's a problem that they're going to want you to do with this. So take some complex number in Cartesian and transform it into polar. So just like you guys have been doing, we want to plot this. Okay, over -3 up 4i. So we grab our equation. How we find a complex number in polar form, the only two things we need are r and theta. Well, the r is going to be really easy to find. We said the r is just the magnitude. So if you put in a right triangle here, simple Pythagorean theorem will tell us this is 5. Remember, ignore the -3 there. So right now, we can throw a 5 in already. Only thing we're going to need is theta now. We're trying to find this guy right here to tell us how far to tilt over to get to quadrant 2. We may have to find this little guy down here. We can call it theta 2 or whatever you want to use there. Now, you can use any of your trig functions because this is a right triangle, but you're just going to have to adjust accordingly. So I'm actually going to do a tangent because let's say we screwed that radius up. We don't want to be using it if it's not correct. So I'm going to say tangent is opposite over adjacent. Go to the calculator. Now, these can be in degrees. Okay, we don't want radians for these. So if I inverse tangent -4/3, it spits out -53 degrees at me. Now, if you remember, inverse tangents are only defined in 1 and 4, so that's why it's telling us that. But we can know that this right here is 53 degrees. Okay? We care about this big guy that tilted us over to there, so if I add 180 to it, 126. That's the same thing as me going, oh, I can take 180 and I can minus 53 degrees from it. Okay? So however you want to get there. Now I know it's 126.8, so all I got to do is go write this in. And that's it. So this point in polar form is the exact same thing as -3 plus 4i.